from Duke University to give a talk on Abelian L functions from explicit class field theory to transcendence theory.
Thank you very much for the warm introduction. It's a pleasure to be here in Philadelphia. So since this is a pretty diverse audience, I want to give a really general overview of just the research that's been motivating me for 25 years now since I started graduate school, and I've been thinking in kind of the same direction. So you'll get kind of like a highlight of what it's like to think about the same thing every day for 25 years, and then finally veer off and screech off on an exit ramp and start thinking about something else, which is what's been happening over the past year or two. So the first 2/3 will be a certain topic, and then you'll see how it's related to something that's very, different, in terms of what kind of mathematics gets used, and those are kind of more recent things that I'm thinking about. All right, so today I'll talk about 3 topics in number theory. So this is sort of a classical motivation for the types of questions I'm going to think about. Special values, explicit class field theory, and so a classical theorem is the Kronecker-Weber theorem. I'll state that in a second, and that goes into the 20th century, the theory of complex multiplication. Actually, the latter part of the 19th century already, complex multiplication was in the works. And then we have Hilbert's 12th problem, which is a very famous open problem in math stated by Hilbert. And then we get into sort of more modern topics in the middle of the 20th century. People start thinking about special values and L functions, and a very famous example is Stark's conjecture. That's the central case of these special values of L functions questions that I'm going to be talking about today. But a more famous example, maybe now that's a little bit sexier now, is because it's related to elliptic curves, is the Burton's miniature diagonal conjecture. Oh, is this on? Yeah, let me do that. Sorry about that. All right. And then the final topic that we'll veer off to at the end, but it's related to L functions. This is kind of a connection between these different topics, is transcendence theory. And there's actually a really important implications of a certain conjecture called Leopold's conjecture for the original topic, explicit classical theory. All right. So let's start really basic. So what are the field of algebraic numbers? So a number is called algebraic if it's the root of a non-zero polynomial with rational coefficients, like the square root of 2 or the cube root of 2. The set of algebraic numbers, the first theorem we prove about this is that the set of algebraic numbers is a field, and we denote that field by q bar. And so so it's natural to ask, what is the set of symmetries of this field? Okay, so what is the Galois group of a Q, which is denoted GQ? So it's just a set of all isomorphisms from Q bar to itself. So for example, the simplest way of making such an automorphism would be you could embed Q bar into C and then take complex conjugation. That would be a very standard order 2 automorphism. Okay, so the Langlands program, which I'm not going to talk about today, it occupies a huge chunk of modern number theory, tries to understand the n-dimensional representations, or more generally the representations into points of a reductive group of this group, GQ. Okay, we're not going to talk about that today. So this is like a representation theory perspective on this, on trying to understand a group, is to understand its representations. But the first step in understanding a group or understanding its representations would be to understand its abelianizations, right? So the one-dimensional representations are homomorphisms into the multiplicative group of a field that's abelian, so it has to factor through the abelianization, right? And by Galois theory, if you have a quotient of a Galois group like the abelianization, then that corresponds to an extension, which is called the maximal abelian extension of Q. So for example, if you want to think about abelian extensions of Q, well, you can think about finite extensions, and when you take all their union all together, it gives you the maximal abelian extension. So how do you make a finite abelian extension of Q? Just as an example, you can take Q would join the square root of an integer. So for example, you can take this Q join the square root of -1, right? And so that's a little degree 2 extension, and the Galois group there is just generated by complex conjugation, and so it's an order 2 group, and Z mod 2 is abelian, so that's an example. And so the question is, like, what are all examples? Well, here's another set of examples. If you take a positive integer n, and you take an nth root of unity, so e to the 2 pi I over n, and you adjoin that to Q, it turns out to be a field extension of Q that is Galois.
and its Galois group turns out to be Z mod NZ star. So basically, a Galois element, so an isomorphism, so what's a Galois group? It's an isomorphism from this field to itself. It has to send zeta n to some power of zeta n. That's not hard to show. And that power has to be relatively prime to n. So that power is the element in Z mod NZ star under this isomorphism. So you can show that's an isomorphism. And Z mod NZ star is an abelian group. So this is another example. And all QAB is just a union of all these fields. So you take Q joined with D and Q joined zeta n, and you throw them all together for all n's and all d's. Well, how much of QAB do we have? Are there other extensions that aren't just these two examples? All right. So the Kronecker-Weber theorem actually tells you what QAB is, and tells you, in fact, that the second example is enough. If you take Q adjoins zeta n for every n, and you take their union, say inside complex numbers or something, then this is all of QAB. Right? So this is a very famous theorem, again, also from the 1800s, that tells you explicitly what QAB is as a field. And so in particular, like this, you might say, well, where's the square root of D in there? I don't see that. So that's the theorem. And the square root of D is contained inside of Q adjoin, zeta n for some n. And it turns out that 4n or 4d works. The square root of D will always be contained inside zeta, so 4d. But not just the square roots, but every abelian extension that you can make out of from the rational numbers will be contained inside of Q adjoins zeta n for sub n. Okay. So now you can try to generalize this. So if you take an extension of Q, that's a finite extension, that's called a number field, and you can look at its Galois group. So you can look at the set of isomorphisms from Q bar to itself that are the identity when restricted to F, and then you can look at its maximal abelian extension. And I want to try to say something about this FAB, right? So we sort of solved this question for Q. We said that QAB is obtained by taking Q and adjoining all the nth roots of unity. You might ask the same question for a general field F. And in order to say something about this, I'm going to need an auxiliary definition, so I'm going to put this at the bottom of this slide, that the ring of integers of F is a subring of F that contains the roots of all monic polynomials with integer coefficients. So just as an example of that, so if F is Q, then I'm saying all rational numbers that are roots of monic integer polynomials. It turns out that integers are the only ones that satisfy monic integer polynomials. So for example, if n is an integer, n satisfies the polynomial x minus n equals 0. Okay, so it's obvious that integers satisfy this, but maybe it's slightly less obvious, and it's a good exercise to try to prove that the only rational numbers that satisfy monic integer polynomials are the integers. So if a over b satisfies a monic integer polynomial, b has to be plus or minus 1. All right. So that's the ring of integers. That's going to come up in the next slide. So what is class field theory? So class field theory, which was something that was developed in the middle of the 20th century, was tried to understand this field FF. So what they found was that there's a structure very similar to what's going on with the rational numbers, which is that there are some special fields that play the role of this Q adjoins zeta n. And so I can't write it down explicitly, but we can just call it Fn. Right? So this plays the role of Q adjoins zeta n. So given a field F, there's a special field extension called Fn, and the name for it, I don't know why I chose such a complicated name, is that narrow array class field of conductor n. But what these fields satisfy, first of all, is that they're like Q adjoins zeta n in the sense that FAB is just the union of all of them. Okay? And they're nested in the same way that if n divides n, then Fn contains FAB. And then the most important part of the theorem is to tell you how big Fn is, more specifically what the Galois group of Fn over F is. And so I won't tell you what that is, but I'll tell you sort of what the Galois group of F1 over F is, which is the narrow class group. So for the algebraic geometers here, I know there's a lot of algebraic geometers, this would be just the Picard group essentially, the narrow Picard group of this ring of integers. And I'll tell you what the Galois group of Fn over F1 is. That's very easy. It's just this, in terms of this ring of integers, it's O mod n star modulo the totally positive units of O. So just as an example, if you plug in Q as an example of F, this applies equally well to Q, even though it's much more general. In that case, your Qn is the Q adjoins zeta n. And I told you earlier the Galois group of Qn over Q is Z mod n Z star. And you can see that from this expression. It turns out that the class group of Z is trivial, so this is just trivial. So F1 is equal to F. And then the Galois group of Fn over F, when F is Q, is Z mod n Z star, modulo the totally positive units of Z. What are the totally positive units of Z? Z's only units are plus or minus 1, and only one of those is positive 1. So you're just modding out by nothing, you're modding out by 1. So there's nothing happening when you mod out here for Z. So you're just getting Z mod n Z star. And that's what the answer was I told you earlier. So this generalizes the picture for Q. Well, what's one thing this doesn't tell you? Go ahead. Yeah.
That you need to have an attribute.
Well, right, exactly. This doesn't tell you what Fn is, right? Even for Q, this tells you this part of the equation, or this part of the information. It doesn't tell you this information. And for Fn, we don't know what Fn is. It's just some field that satisfies a bunch of properties, right? And that's the question of explicit class. So that's where the word explicit comes from, which is that we know what the Galois group of F over F is. It's the inverse limit of these Galois groups of Fn over F, which I kind of described a little bit in the previous slide, right? So we know what the Galois group is, but we don't know what the field is. So we don't know what F is, or equivalently what each of the fields Fn are. So you really want to have some description of what Fn is in terms of analytic functions depending only on the ground field. That's kind of the yoga of this. So you want to have, if you don't want to feed in information that kind of knows the answer, you want to have something that only knows the ground field F, and then from F spits out this abelian extension. So for example, for QAB, we know what QAB is. It's you take this analytic function e to the 2 pi ix, and you plug in special values, and then it spits out extensions that give you the maximum abelian extension. So you put in, and this is maybe a coincidence or not, the values that you plug in are the field itself, in fact. You plug in the values of Q into this analytic function, e to the 2 pi I over e to the 2 pi ix, and you get all of QAB. That's a very beautiful presentation that's linking something that seems analytic, this holomorphic function, and its special values, to something that's sort of algebraic and number theoretic, which is like how do you generate the maximum abelian extension of Q. And so this is what you kind of like to model the general answer on. And the case that was done next is the case of quadratic imaginary fields. So you take Q adjoint I, so Q adjoint the square root of -1, or you take Q adjoint the square root of -2, -3, won't say -4 because that's the same as Q adjoint I, but -5, etc. We know how to generate the maximum abelian extensions. And what comes up is the theory of modular forms, or modular functions. So there's the theorem that Fn, I can write down exactly what it is. It's F adjoint the J invariant of an elliptic curve with complex multiplication by the ring of integers in that quadratic imaginary field, together with what's essentially the coordinates of the n torsion points of that same elliptic curve. This Weber function is some technicality having to deal with the primes 2 and 3, but it's basically giving you the coordinates of the n torsion points. And so J here is the modular function on the upper half plane, the usual one. Has this Q expansion. And so what we see is that for quadratic imaginary fields, modular functions, these analytic holomorphic functions on the upper half plane, play the role of the exponential function for Q. Right? So these modular functions are doing what Q did. So you're taking these modular functions and when I say J of E, you can think of this as J of tau for a particular tau in the upper half plane that corresponds to F. So you're plugging in special values of the field. In fact, the values again are the values from the field. If you think of the points in Q adjoint root -d that live in the upper half plane, and you plug them in to these modular functions, once you translate what it means to take the Weber function of the n torsion points, that's just a modular function evaluated on the upper half plane. If you take all these modular functions together with the J function, you evaluate at all the points in the field, you're getting the maximum abelian extension. Okay? So these holomorphic functions are playing the role of the exponential function. All right, so how do we do this in general? And that led Hilbert to his 12 problems. So it is very famed ICM address in 1900. So we're having an ICM here in Philadelphia next year, so hopefully you'll all go and someone states 23 questions that are as profound and influential as Hilbert did. Well, we'll hold our breath for that. But in the meantime, we can think back on Hilbert's original problems dating 1900, many of which are still open, including the one smack dab in the middle, the 12th problem. He says, so these are some excerpts translated from German, so very selectively chosen excerpts to kind of make the case for my talk today. So the theorem that every abelian number field arises from the realm of rational numbers by the composition of fields of roots of unity is due to Kronecker. So this is the Kronecker-Weber theorem that I said, that QAB is the union of Q adjoin zeta n. Right? So this is, he's saying, okay, we got this theorem, it was great. Since the realm of the imaginary quadratic number fields is the simplest after the realm of rational numbers, the problem arises to extend Kronecker's theorem to this case. So at this point in 1900, the theorem of complex multiplication that I wrote on the previous slide hadn't been proven, but it was in the works. Like Kronecker was doing it, he called it his Jugendtraum, his dream of youth, was to sort of prove this theorem of complex multiplication and sort of get it right. And I think some of the issues was getting exactly this Weber function of the n-coordinate of the torsion points. So Kronecker was really working with the J function, and he really wanted to nail down what's the maximum abelian extension of a quadratic imaginary field. And Hilbert sort of realizes that Kronecker basically has it. He say, okay, Kronecker, you basically got it. Like, let's finish this up and tie it with a bow and finish. Okay, but now once you do that, let's move on. Finally, the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or the imaginary quadratic field, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. So already in 1900, it was recognized by Hilbert that this is really, you're walking up to the edge of some line, even when you solve the quadratic imaginary case, that there's something we really fundamentally don't know how to do once you get beyond that point, that we don't know how to break into any other base number fields as our f's that we're trying to generate the abelian extension of. And he says that's going to be much harder. And this may remain a central motivating question in number theory for over a century. Okay, so what is the modern approach to this? So a modern approach, now I'm finally going to be talking about L functions, which are like the first part of the title of my talk. So I've given the motivation via explicit class field theory, and now we're going to get to L functions. So before I talk about L functions, I should talk about zeta functions, which are the simplest example of L functions. So it turns out that each of these rings, these rings of integers, which I call O, satisfy a property that for every non-zero ideal, the quotient of that of the ring by that ideal is finite. Okay, we call that the norm of the ideal. And from that definition of the norm of ideal, we can define what's called the zeta function of the ring, or zeta function of the field for short, which is we take the sum over all non-zero ideals, the reciprocal of the norm to the s power. Okay, so just the simplest example is if f is q, then the non-zero ideals of the ring z. So remember, O is just z in that case, the ring of integers. The non-zero ideals of z are just generated by positive integers, right? Each positive integer generates an ideal. What's the size of z mod nz? That's just n. So you're just taking the sum as n goes from 1 to infinity of 1 over n to the s, which is just the usual Riemann zeta function, right? So in general, this is some generalization of that. So let's just do the example of q adjoin I. For q adjoin I, the ring O turns out to be z adjoin I, so instead of a plus bi, where a and b are integers. The ideals are again principal, so they're just generated by m plus ni, where m and n are sub-integers. And that's a non-zero ideal if m and n are both, or either one of them is non-zero. And what's the norm? What's the size of z bracket I modulo the ideal generated by m plus ni? You draw a nice little picture in the plane, you have a little square generated by m plus ni and all of its unit multiples. And then you take the area of that square, it's just m squared plus n squared. Okay? So you get 1 over m squared plus n squared raised to the s powers, m and n range over all non-zero pairs. But of course you've overcounted because I said you can multiply by unit multiples, and the units in z bracket I are plus or minus 1 or plus or minus I, so you have to divide by 4. So you've counted each ideal 4 times. It'd be like if I'd gone over all non-zero integers, then you'd have to divide by 2, right? You have positive and negative n. All right, so that's two examples, and just like the case that you've probably seen for the Riemann zeta function, it has a product formula, the Euler product formula, over all the primes of 1 over 1 minus p to the minus s. There's a similar thing if you take a product over all non-zero prime ideals of this general ring O. Those are all happen to be the same as the set of maximal ideals, then you get 1 over 1 minus norm p to the minus s. So that's a nice expression for the zeta function. Okay. And now here's a beautiful theorem, which harkens all the way back to, so a lot of stuff, in this lecture goes back to the 1800s. Dirichlet proved this in certain cases, and Dedekind, who generalized it for the general setup I have here for a number field, is to take this zeta function. So that sum, which I wrote down, the sum of 1 over norm of a to the s, that converges actually only for real part of s greater than 1, for complex numbers s with real part greater than 1. But there's a theorem that there's an analytic continuation of that function to an analytic function on the, or to a meromorphic function on the entire complex plane, and so you can ask for its value at 0. And it just makes this formula a little bit easier. And it turns out that this has a 0 at 0, and the order of that 0 is exactly the rank of this unit group, the group of units of O. Okay, and I'll just point out, maybe I'll say something. What makes the two cases that we know how to do explicit class field theory special, Q in quadratic imaginary fields, this little r is 0. Okay, and those are the only cases where little r is 0. For all other number fields, little r is bigger than 0, it's positive. Okay, and that's really where you get a breakdown in trying to generalize. Okay, but anyways, so once there is a 0, so maybe r is 0, so this works even if r is 0, but for all, no matter what little r is, you can say that there's a 0 of order r, and the leading term is negative hr over w. Okay, what is order hrw? So h, something I've alluded to before, is the size of the class group, so this is the size of the Picard group of O. R is a regulator. I'll say what that is more later, and it's going to play a big role at the end of the talk. And W is the number of roots of unity in L. Okay, so it's just some integer. And so this is a really cool theorem. So a lot of people think this is cool because it's linking something analytic and something algebraic. But really, the depth of this conjecture is not about the fact that it's linking something analytic and something algebraic. The depth of the conjecture is that it's linking something locally defined to something globally defined. That is, we're taking really special and simple, in some sense, information about the ring O. We're taking all of its maximal ideals, and we're taking the size of the quotient of O modulo that maximal ideal. That's just some integer. And then we're packaging them into some weird function. We're taking the product of 1 over 1 minus that integer to the negative s power, and we're making an analytic function out of it. But it's just taking this local information. So local number theory means like modulo primes, right? So we're just taking the size of the ring modulo prime, not even any interesting deep information about the ring, just the size, right? And then we're making a function out of it, and then we're taking a special value at some point, and we're getting these deep global invariants. So you can't know what H is or R is unless you know the whole ring O. Like you can't just look at it modulo sub prime and then figure out what H is, right? So it's a passage from local to global, and this is kind of, so Barry Mazur wrote an expository article, which I read when I was in undergrad, about the passage from local to global number theory, which is very influential to me in terms of how you think about the depth of these conjectures about L functions that are really about passing from local information to global information. You can view the Birch-Swinton-Dyer conjecture as the same thing. The L functions are made out of local information, elliptic curve modulo primes, and you get some deep information globally, like the rank of the Mordell Bay group of that elliptic curve. All right. Now, to talk about explicit class field theory, we need to generalize. So far there's only been one field involved in our L function, it's just f itself, an int ring of integers. To get to generalize and to talk about these extension fields Fn, you need to take some representation theory perspective, which is, well, so let's take a character of that Galois group. So take the character of the Galois group of Fn over F, okay, and then use that character to generalize our definition of the zeta function. So it turns out that for every maximal ideal that doesn't contain the integer n, when I'm thinking about Fn, for every maximal ideal that doesn't contain n, and it turns out there's only finitely many that do contain n. So if you take out those finally many, there's a special element of the Galois group called the Frobenius, which is denoted as sigma sub p. And then using that Frobenius and this character you've chosen, you can get this root of unity, chi of sigma p. And you can generalize the definition of the zeta function by sticking that in front of the norm. So instead of taking 1 over 1 minus norm of p to the minus s, you take 1 over 1 minus chi of sigma p times norm of p to the minus s. Okay, so this is the way to generalize it. And so if chi was the trivial character, this is just 1. This really would just be the same zeta function, except you're excluding those finally many products of factors where p contains n. Okay, so that's just a generalization. And then Stark gave a conjecture which is motivated by that class number formula where you have a regulator. So I didn't tell you what the regulator was. I'll tell you in a bit later. But it's a determinant of a matrix where you have logs of absolute values of units of the number field. So we said something like this should happen for these general functions, these L functions, that are generalizing this zeta. So we make an assumption, by the way, this is kind of a technical thing, that you fix an embedding of fn into the complex numbers, and you assume that if f lands in the real numbers, then fn does too. And what that assumption does is, if f doesn't land in real numbers, there's no assumption, and this automatically holds, is that all of these ln of chi's are 0 at 0. If you plug in 0, you get 0. So it makes sense to look at the derivative. And since we're looking at the first derivative, you have like the determinant of a 1-by-1 matrix, which is just a number. And so in place of the regulator, you have the logarithm of a single unit. But since we've introduced this character chi, he wants to take the sum over all elements of the Galois group of chi sigma weighted by the conjugate. Okay, and that's Stark's conjecture. He says there exists some unit in the extension field such that if I take the logarithm of all of its conjugates and take the absolute value and just take a twisted sum, right, weighted by a character, then I actually get the derivative of the L function of that character at 0. So this is a really deep and open conjecture. Nobody has any idea how to prove this. Okay, it's been open since, I don't know, so he made this conjecture over a series of years, but probably the early, ideas of it were the very early 1970s. So this is at least 50 years open question. All right. Now let me link this to my original question about class field theory, explicit class field theory. What does this have to do with it? So if you go back, you can solve all these equations back. That is, the number of equations here is the number of characters. I've written one equation for each character. The number of characters is the size of G, right? And that's the number of conjugates. So you have same number of linear relations as you have equations, and you can show the system is, doesn't have determinant 0. So you can solve back, and you can find what log of absolute value of sigma of u is for all sigma, okay, if this u exists. And then you can exponentiate and get the absolute value of sigma of u. Okay, and so at the end of the day, you get the absolute value of sigma of u for all sigma. And first, if you fix one embedding of your field into the complex numbers, like what you've done, then if sigma is the identity, you're basically just getting the absolute value of u, right? So what would be really nice is to not just get the absolute value of u, but to get u itself, right? Because then I'd have an actual formula. So it'd be like, oh, the j function evaluated at some point in the upper half plane. I'd get an actual formula for the number I cared about. This number that's living in this extension field, right? This u lives in the extension field Fn, and that's the thing that we don't know how to construct. And that was really one of Stark's motivations. It's like, we don't know how to construct these extension fields, but I'm telling you via some conjecture that there's a really special element up there called u. Okay, just call it u so that somebody else can come along and call it Stark's unit. So there's some u up there that's Stark's unit that satisfies the property that it lives in this extension field that you're trying to construct. And you know how to write down something about it, its absolute values, using analytic functions that only depend on the ground field. So this L function of chi, we know how to write it down without knowing what Fn is, right? And that's what we want. We want some analytic way of writing down elements and extension fields using information only intrinsic to the ground field. So, but this absolute value is a little bit annoying. It represents a gap between Stark's conjecture and Hilbert's 12th problem. If we had a way of writing down what u was rather than just this absolute value, there would be a way of constructing non-trivial elements of Fn. And there are interesting conjectures in this direction by Leninchek and Charlotte Darmon. And I have a student named Kyrie Black who is just generalized this conjecture of Leninchek and can basically do it for any ground field F for which the conjecture is non-trivial, which is these so-called ATR fields. You need some control over F. I mean, it turns out, so basically when I say trivial, okay, if this derivative is 0, then you can take u to be 1. This is a trivial conjecture. There's a non-trivial conjecture then, in that case, using the second derivative. We don't know how to do anything there. But for this first derivative conjecture, Kyrie has a generalization of the conjecture that would state a formula for u rather than for the absolute value of u, which would be awesome because then you could try to generate these field extensions. Unfortunately, it's just a conjecture. She doesn't know how to prove the conjecture. That would be a miracle if anyone could. If you prove this conjecture, we probably would have built them. But anyways, let's move on. So, okay, so what can we prove? Right, so derivatives of L functions and logarithms of units is really outside of our scope of what we can handle, right? We need to get a handle on things, and we need to get cohomology into the picture. So there's another conjecture which is related, which doesn't have which doesn't have derivatives of L functions, but just values of L functions. And those are easier to handle because these are algebraic numbers. These are not crazy transcendental things like logarithms of units. Okay? So there was a conjecture, and I'll give you the history of this conjecture, but it's called the Broomer-Stark conjecture because it's motivated by the Stark conjecture that I just stated. Okay? Where instead of the derivative of an L function, you have the value of an L function. So we're in a different situation where we don't have that assumption at the beginning that makes the L functions automatically vanish, like automatically be 0, so that then you look at the derivative. We're in a different setting where the L values are not 0, so these are interesting numbers. And so you ask, can that L value be equal to, and so you don't have the logarithm of a unit here, you replace the logarithm with just the valuation at a prime, right? So the valuation of prime means like the valuation of the number 18 with respect to the prime 3 is 2, because 3 squared divides 18, right? And so that's what this OR is, it's just the valuation with respect to this prime. So you take so instead of kind of the infinite place, where you're taking a logarithm of an absolute value, you're taking a finite place and just looking at its valuation. So you take a finite prime p in your ring of integers of your ground field, and a prime that divides it in the upstairs field, and you conjecture that you have a unit upstairs that's not a unit, but it's a p unit. Okay, so kind of the role of infinity is being played by p now, and it has absolute value 1 at every Archimedean place, and such that the valuations of this unit, or in all of its conjugates, are given by the values of the L functions. So this is very similar to Stark's conjecture, except instead of derivatives, you just have values, and instead of logarithms, you have valuations at a prime. Okay? Now, to make the conjecture correct, the right side is clearly an algebraic integer. These valuations are integers, that's it, define them, and these are roots of unity. So this is an algebraic integer. So you better have the left side being an algebraic integer. And it is an algebraic number, but it's not an algebraic integer with just L of chi 0. You need to scale it by some smoothing factor. This is sort of idea behind this comes from Deligne, really. And so once you multiply it by this, Deligne and Rivet prove that this is actually an algebraic integer. So there's a hope that an equation like this could hold. Once you've introduced this prime q to make this smoothing factor, you have to have an extra condition at that prime. The extra condition is that u is congruent to 1 modulo of that prime. Right. So that was called the Broomer-Stark conjecture. Let me give some history about it. So again, like everything else in this talk, this goes back to the 1800s. So Stickelberger in the late 1800s, I think it was 1898, so just squeezed it in for the end of the century, he proved that formula in the case where the ground field is Q. Okay? In that case, he knew what the unit was. It turns out to be a Gauss sum, right? These sums of, of products of roots of unity with, so basically, sums of roots of unity, which are Gauss sums. And his question was, what are the valuations? these things that show up in the formula, like what's the valuation of this Gauss sum? And what he showed was that the valuation of the Gauss sum was related to the L value, right? So he proved that, this Brumer-Stark conjecture before Brumer or Stark were born, because it didn't have that name yet, but he just proved this formula, that the L value was equal to this linear combination of valuations of Gauss sums. And it was Brumer who in the 1960s gave a series of lectures that said, for general totally real number fields, we should have a similar phenomenon, that there should be similar elements. We don't know that they're Gauss sums anymore. There should be similar elements whose valuations, if you take their linear combinations with the character chi, give you the L functions. Okay? Stark stated his conjecture about the derivatives, which I told you in the previous slide before I presented the Brumer-Stark conjecture, but it was actually Tate who stated the conjecture in the form that I gave it. So Brumer's conjecture was a little bit imprecise, and one thing that Tate did is he stated it very precisely, and he incorporated this auxiliary prime Q in a way that Brumer had not done, which comes from studying Stark's conjecture and saying, hey, if you smooth it with this factor, you can actually get equality, and your unit U should be congruent to 1 modulo Q. That was really Tate's idea, to put that into the conjecture, and that came out of studying Stark's conjecture, because there's an analog. I didn't state all of Stark's conjecture, but there's basically an analog that has to do with that smoothing prime Q. And so Tate said that same idea should work in Brumer's setting. And so, you might think we should call this Tate's conjecture, since he's the one who stated it, but that name was maybe taken already. So, so he called it the Brumer, so very generously called it the Brumer-Stark conjecture. Okay. So, how do you try to answer questions like this? All right, so the punchline, I think I say this on a later slide, but I'll just give it away now, which is that, so one of my recent works with Mahesh Kakde, and the most recent part of it is with two of my postdocs, who were postdocs, no longer postdocs, Julia Wang and Jesse Silliman, which is that we've proven the Brumer-Stark conjecture. So that was, so it's a theorem now. And what is the method for doing that? So how do you connect L functions, or special values of L functions, to things like class groups or units? Okay, so class groups and units are closely related. For the reason, for example, if you have it show that something is trivial in the class group, then it's a principal ideal, which means it's generated by an element, and then you know the control of the primes dividing that element based on how you created the class, like what ideal created the class. So this is a nice way of making units, and if you really understand class groups, then you can generate units, or p-units, and that's how we prove the Brumer-Stark conjecture. So how do you link L functions and class groups? So this is a method that goes back to Ribbit, and I'm not going to have time to give you obviously all the details of our proof. But let me just give you the web of deep structures of number theory that are used to connect something like L functions and class groups. So modular forms. Modular forms have shown up already, but this is a very different use of modular forms. So there's certain modular forms called Eisenstein series, and the relationship between Eisenstein series and L functions is that the constant terms of Eisenstein series are L functions. They're special values of L functions. That's how you realize L functions as living in the world of modular forms. Now, from Eisenstein series, you can make cusp forms. So for those of you that have studied modular forms before, the very first cusp form that you make is the delta function. How do you make it? You take E4, the Eisenstein series of weight 4, and you cube it, so you get into weight 12. You take E6, the Eisenstein series of weight 6, and you square it to get into weight 12. And then you just subtract them in such a way that you cancel their constant terms. And so now you have a constant term of 0, which makes it a cusp form. Okay. That's the same thing that Ribbit does. He takes linear combinations of products of Eisenstein series to cancel out constant terms and make cusp forms out of them. And why do you want cusp forms? Because this is where the really, really deep thing happens. This is where you go from something that's inherently analytic, the modular form, to something that's algebraic, something that knows a Galois group, which is the Galois representation associated to a cusp form. So this is super deep, and this comes from work of many, many, many people, like maybe first Deline, Deline and Sayre, and then Carriol and Wiles, and Ribbit, originally in his case where he could make the Galois representation from the Jacobian of the modular curve, and Taylor, and Hida, so many names that have gone into making Galois representations out of cusp forms. Okay, this is one of the directions of the Langlands program, and so the so-called easier direction, which is still really, really, really hard. Okay. Okay. From Galois representations, we can make Galois cohomology classes. If a Galois representation is reducible modulo some ideal, then you can produce a Galois cohomology class from it. And the reason that it would be reducible modulo some ideal is because of the way that you constructed the Cuss form is that modulo some ideal is congruent to an Eisenstein series. And so therefore modulo that same ideal, which the Galois representation should be reducible, since the Galois representation of an Eisenstein series is reducible. Okay. So these are generically irreducible, but modulo some ideal are reducible. And in that exact situation, Rivet showed how you can make a Galois cohomology class. And Galois cohomology classes are related to class groups via class field theory. So in Rivet's context, it was basically Kummer theory, and there's general theories due to Ritter and Weiss that generalize this connection. Okay. So that was obviously, no details of any proofs or anything, but I just wanted to show all the different ingredients that go into proving a theorem like this, and how the whole weight of modern number theory is like brought to bear on proving a very particular conjecture. Like each of these arrows is a very deep subtopic within number theory. Okay. Now, dealing with the case of p equals 2, so I didn't say what p is, but we kind of work locally at each prime. And p equals 2 is particularly difficult in the proof of the Brumer-Stark conjecture. And that was the most recent thing, the thing that I mentioned that we brought two of my postdocs on to help us with. It's really deep, and I wanted to mention it here because I know there's a lot of people from different fields, and this might relate to something that you're doing that has nothing to do with number theory. But so we have to prove what's called a residually indistinguishable case for Rivet's method, which we only do for GL2. And so some ingredients that come in that weren't present before are matrix invariant theory and Hochschild cohomology. And something that I'm like really glad I remembered from grad school when I was doing this, because I had a student do some computer computation to try to split some co-cycle. And there were all these things that looked like wedge products. It was like, A1, B2 minus B1, A2. And I was like, oh, that looks like an exterior power item. It reminded me of the Kosohl complex, and that turned out to be exactly what we needed. And there's a generalization that's much less well known due to Buxbaum and Rim. And so these like kind of structures that I remember from like second year of grad school or whatever came back like 2.5 decades later to help prove this theorem. So I'm very glad I had my nose in Eisenbud for some period of time when I was in grad school. All right, now I want to just link this back up to the original motivation. So I said we proved the existence of these special units, U. Okay, but what does that give you? Well, it turns out there's something further. I said, oh, it'd be great if we had a formula for U and not just the absolute value, right? And that same hope is there in the Brumer-Stark case, too. It would be great if we had an exact formula for this unit rather than just its valuation, right? Rather than just its order. And that actually, stating that formula was my PhD thesis. That's how I got involved in this mess. Was for my PhD thesis, I stated a conjecture for, it's kind of like an analog of what Kyrie's thesis is now. Kyrie's working in the Archimedean case, I was working in the p-adic case, which is, can you state an exact formula for U rather than just its valuation, which is what the Brumer-Stark conjecture gives you. And so I stated that conjecture, and it turns out that using the same methods, building upon some extra ideas, we can actually prove this conjecture. So I proved an exact formula for these units as a sort of p-adic multiplicative integral. I don't have time to get in to explain what that integral with an x through it means. This is notation of Darmon who invented this idea, but it basically means you take a Riemann product instead of a Riemann sum when you're doing your integral, which behaves nicely in the p-adic world. Okay, and the point of this is that this is actually, computationally feasible. So I had two undergrads at Duke code this for me a few years ago, and they could actually write down these p-adic integrals and take the elementary symmetric products of these elements and then recognize them as algebraic numbers, and you get some polynomial. And then, so you haven't told the computer the field you're trying to construct. So we just did the simplest case of n is 1. So we're trying to construct F1 with the prime p equals 3, and you write down this polynomial, and the computer didn't know what the field is, but you say, hey, look at this field, And you show that it's actually a Galois, generates a Galois extension with an abelian Galois group by somewhere with Z mod 4Z, and you can check that it's unramified everywhere. It is the narrow Hilbert class field. So you constructed F1 without telling the computer F1. You just told it the number 1 and the field F, and then it produced this polynomial. Okay, so it produces the field for you. So it really is explicit class field theory. Here's another example. You would join course over there. When you go to an example where I can get the narrow Hilbert class field to be Z mod 6Z, and then so here's, you can see the numbers get big pretty quickly. Okay, so how much of the maximum abelian extension of F do you get with these units that we now know how to write down explicitly using these integrals? Turns out all of it. So if you write down all the Brumer-Stark units, and then you throw in some special square roots that are really easy to write down, there's just elements of F, square roots of elements of F that have all possible signatures, you get the maximum abelian extension. So we basically solved the question of can you write down analytically the maximum abelian extension of any totally real number of fields. So because we proved this, and we proved these U's exist, and we proved this analytic formula. Okay. Let me actually skip this. So this is like what extra ingredients do you need to prove the formula more than what you used for Brumer-Stark. And I'll just say this integral version of a conjecture of Gross due to Popescu that we proved, Popescu and Rubin, and involved in linking the exact formula with Popescu. This conjecture is this the Taylor-Wiles method of horizontal Iwasawa theory. But I really don't have time to say anything more about that because I want to move on to a different topic. Okay, so if you zoned out a little bit for all the explicit class field theory stuff, you can come back because it's now a new topic, which is the topic of regulators. Okay, so I glossed over this when I told you the value at zeta at 0. It was there's some derivative, and that it was HR over negative HR over W. Okay, so I didn't tell you what R is. I just told you that it was some matrix. And again, I won't tell you many of the details. First of all, I want to say that I'm saying this at the residue S equals 1 rather than the value of S equals 0 for a reason that will become clear in a moment. But traditionally, actually, that's how it's presented. This tilde is doing a lot of heavy lifting here. There's a lot of other factors if you want to make it equality, but they're kind of specific things you can write down easily, like powers of 2 and 2 pi and square root of the discriminant, stuff like that. I just want to gloss over it. The really interesting parts are the class number and the regulator. So what is the regulator? It's basically you take a basis of the unit group of O, and you take all possible embeddings of your field into the complex numbers, and you only count like a complex conjugate pair once, and then it turns out there's one more embedding than there are units, so you cross out one column, and you take the matrix that remains, and it's a square matrix, you take its determinant. And the elements of the matrix are the absolute value of the logarithms of the consequence of E, the exact same things that were showing up in Stark's conjecture. Okay? And a really deep theorem is, well, deep, I mean, you can prove it in an undergraduate number theory class, but it's not obvious, is that the regulator is non-zero. Okay? So it feels like it's actually much deeper, but like I said, you can prove it in an undergrad number theory class, because once you break out of this regime of this particular case, we don't know how to prove any generalizations, basically. So just as an example, Comes has proven a p-adic class number formula. So we take the p-adic zeta function, and you conjecture that it has a residue. I mean, what he proved is that the limit as s goes to 1 of s minus 1 times this is equal to the class number times the p-adic regulator. And we think that it's a residue. That is, we think there's a pole because we think that this number is non-zero. That turns out to be an incredibly deep conjecture due to Leopold. So this determinant of p-adic logarithms of units, we think that it's non-zero. Okay? We know how to prove that. So this is a theorem somehow that like the limit as s goes to 1 of s minus 1 times this is equal to h times rp, but we don't know how to prove that rp is non-zero, in which case it really would be a pole and a residue. Okay. And that's what really got me motivated in thinking about this. And so I said, okay, let's take a huge step back forget p-adic logarithms, just look at regular logarithms. When can a matrix, just take the simplest case, a 2 by 2 matrix of logarithms of algebraic numbers, when can it vanish? Even if these are integers, forget algebraic numbers. What if a, b, c, d are integers? We don't know the answer to this question. We don't know if I take log of a, log of b, log of c, log of d, when a, b, c, and d are honest integers. 2, 75, 800, 432, right? Random numbers. We don't know to say that that determinant should be non-zero. Log of a, log of b, log of c, log of b, right? If that determinant, so the conjecture is that if the determinant is 0, then either the rows or columns of m are linearly dependent over q. So obviously if you take log 2, log 3, log 4, log 9, that determinant is going to vanish because one row is twice the other row, right? They're linearly dependent, right? We don't know how to prove that the only way that a determinant like that can vanish is if the rows or the columns are linearly dependent over q. Okay. Right. Obviously, it can only happen if the rows and the columns are linearly dependent over C, that's linear algebra, but over Q, we don't know how to prove that. Okay. You can make a similar conjecture with the p-adic logarithm. So what's the standard approach to this conjecture? Okay, so you take the vectors a, b, and c, d. So these are two vectors in q bar stars squared. So these are non-zero algebraic numbers. Okay, and you look at the box of size n in q bar squared, where you take all powers of this vector times all powers of this vector, where the powers are between 0 and n. Okay, so that's a set that if they're not like 2, 3, and 4, 9, then this set should have size n squared, right? 2, 3, and 4, 9, you'd have some overlap here, right? And so you wouldn't get as many elements in this set. That's kind of the punchline of the conjecture, which is that if your original determinant is 0, then for n large, there exists a polynomial whose degree is less than n, and such that f of z is equal to 0 for all z, and forget this 2 for a moment, and x of n, right? So if these are linearly dependent, so say it's 2, 3, and 4, 9, then there's only big O of n elements in this set, because 2, 3 squared is 4, 9, which you already have. So you're kind of over-counting. You're getting a lot of overlap, and instead of O of n squared elements in the set, you're going to have O of n elements. So making a polynomial of degree n that has those elements as roots is not a big deal, because you have n squared monomials in a polynomial in two variables of degree n. You have n squared monomials to play with, and you have n roots that you need to have. N squared is a lot bigger than n, you can make a polynomial. If they don't line up like that, if it's not 2, 3, and 4, 9, then you have n squared monomials and n squared elements. You're not going to be able to make a polynomial degree less than n that has all these as roots. So generically, you should be able to make a polynomial. If they line up, you should be able to make a polynomial. So that's the basis of the conjecture, and I think you need a little factor of 2 to give yourself some extra room to prove this. So if you could prove this conjecture, then you would have proved the 4 exponentials conjecture. But no one knows how to construct a polynomial like this. Okay, big open question. Okay, so an idea that Mahesh and I had was actually looking at the degree. Bounding the degree is a little bit too strong. What you should try to do to make your life easier is to find a polynomial that has fewer than n squared non-zero coefficients. And because, right, that was the logic behind why a polynomial of degree n should not exist, because there's only n squared monomials that you have to play with, right? So generically, again, this shouldn't happen if you have a polynomial fewer than n squared non-zero coefficients, right? And it turns out you can show that this implies the 4 exponential conjecture as long as your logarithms are taking value in R, or if you're using the p-adic logarithms. You're taking general algebraic numbers using complex logarithms. I don't know exactly if this condition implies 4 exponentials conjecture or not, but if you could prove this, it would be a massive breakthrough. Like I said, even for integers, let alone, algebraic numbers that are real, literally integers, we don't know how to prove that 4 exponentials conjecture. Of course, the logarithm of positive integers is a real number, so you would be good, and that would be a massive breakthrough. So we don't know how to do this. Okay. And so I should say, okay, now let's talk about going beyond the 2 by 2 case. It's not true that for n by n matrices, you expect the conjecture to be if you have an n by n matrix of logarithms of algebraic numbers and the determinant vanishes, that we expect the rows or columns to be linearly dependent over Q. That's no longer true. You can give examples where that's not true, okay? So we know that that's not true. So one of the deep things that Mahesh and I did was, what should the conjecture be for the n by n case, okay? And this is a conjecture I like to advertise. It's a new conjecture called the matrix, what we call the matrix coefficient conjecture, which says that if you have an n by n matrix of logarithms of algebraic numbers whose determinant vanishes, then there exists non-zero rational vectors such that you multiply on the left by one vector and on the right by another vector, you get 0. Okay, so this comes to the language of modular forms. People call this, in the Langlands world, is called this a matrix coefficient. I mean, it's basically if you change bases and then it is a coefficient of your matrix in that new basis. Anyways, so right. So So it turns out that this conjecture, on the one hand, let me go to the second theorem first. On the one hand, it's implied by standard very deep conjectures in transcendence theory. The Chanuel's conjecture in particular implies it. Okay, so it's expected to be true. But Chanuel's conjecture is really, really hard. Like, this is the uber conjecture in transcendence theory. Nobody has any idea how to even make progress. Whereas this is like a little, I mean, it's still deep, but it's like a little, very easy to say conjecture just about matrices and the existence of vectors. I don't know, it seems like much lighter, okay? For example, I don't know how to prove any of the reverse implications of this. So it seems, I think it's weaker. But it's strong enough to apply a Leopold's conjecture, the p-adic version, right? So this n is the matrix of p-adic logarithms of algebraic numbers. You can state a conjecture like this, that the p-adic version applies Leopold's conjecture, and the conjecture that I'm really interested in is called the Gross-Kuzmin conjecture. All right, so I'm basically out of time. Let's go a couple minutes over if that's okay. So it turns out that, so I want to have a condition in terms of auxiliary polynomials that mirrors what I wrote before about conjectures with few non-zero coefficients. So it turns out that the number of non-zero coefficients isn't very flexible. It doesn't work very well in algebraic geometry when trying to prove stuff. So, but there's something that's very closely related called the Bernstein-Kushnarenko number. So if you have a bunch of polynomials and n variables, you can define the Bernstein-Kushnarenko number as the mixed volume. So this delta is, you take all the monomials that show up in each of these coefficients and you plot them as lattice points in n-dimensional space. You take the convex hull of that, right? So it comes up in toric geometry. And you take the mixed volume of those polytopes, you multiply in factorial. Then the Bernstein-Kushnarenko number of f is defined to be the maximum as I goes from 1 to n of sort of I copies of f and n minus I copies of just a generic linear polynomial. So the auxiliary conjecture, or the conjecture with auxiliary polynomials, now you take the same setup where you take these vectors and q bar star to the n now instead of just 2, and you look at the box of size n. Then what you want to make, assuming that the determinant of m is 0, a polynomial such that the Bernstein-Kushnarenko degree of f is less than n to the n and vanishes on x of n. And that conjecture, the existence of this auxiliary polynomial, you can show implies the matrix coefficient conjecture. In fact, it's equivalent. Yeah, it goes the other way too. So this is really the auxiliary polynomial that one wants to construct, and unfortunately, I don't really know how to do this even in the n equals 2 case. But I really feel like this is the right approach to understanding these deep conjectures in transcendence theory, like Leopold's conjecture about studying the non-vanishing of regulators. I'll end there.
Does anyone have questions for Shulman?
Is there any intuition for why the 2x2 case is special for the logarithm matrices?
Why it's special in terms of the conjecture, maybe that the rows or columns are linearly independent. I don't know. I mean, you can say that. So my conjecture. Oops, right here. This conjecture works for any n. you can kind of see that for 2 by 2 matrices, this condition on the existence of these non-zero vectors is equivalent to just the rows or columns being linearly dependent over Q, but it's not true once you get to higher dimensions. It's easy to kind of write down examples. So for example, you could write down a skew symmetric matrix, like in a 3 by 3 case. You could write down a skew symmetric matrix that is logarithms of algebraic numbers. So the determinant has to vanish, but you construct in such a way that the rows and columns are not linearly dependent. Okay, so 2 is just a little bit too small. Okay. Yeah.
So this determinant, can you regard it as some type of volume of something?
Yeah.
And then you're basically trying to prove that volume is non-zero as a special case or something. Like I guess I'm looking for is there some sort of geometric interpretation of this?
Yeah, I mean,
I don't know too much about this, but there's all this kind of like fancy stuff about like volumes of like stuff like with arithmetic three manifolds, and then like these volumes turn out to be volumes, these determinants of like volumes of certain arithmetic three manifolds and things like that. Like, is there some type of connection with this stuff to that, or no?
Sure, yeah, I mean, there's a connection between L values and these volumes, but I mean, yeah, saying that it's the volumes non-zero is basically saying that things aren't lining up, you know, aren't linearly dependent, and so that's kind of like restating what it is that we're trying to prove. But yeah, it's
I understand, like, it's making it seem more complicated, but I'm wondering if there's some like other interpretation of it that's more geometric in some sense. You know?
That'd be interesting to explore. Yeah, I mean, the translation to geometry that I know of is tautological, and so it's not, you know, I can't see how to prove that it's non-zero from that. But if there's a connection to volumes of objects that we know, or have non-zero volume, that would obviously be interesting.
Could you go back to the next slide? Do you need any conditions on these Newton polyhedra?
Do I need addition?
Or for you to make the link between this and your conjecture?
The condition is what we want. We want a polynomial such that all of these mixed volumes are less than n to the n. So you want a polynomial such that all of these. So for even in the n equals 2 case, it's the mixed volume is just the volume, and the other one is just the degree, right? So there's only 2 invariants there. You take ff, or you take f in a linear polynomial, right? So f in a linear polynomial gives you the degree. So you're saying the degree is less than n squared, and just the volume is less than n squared. If you could make a polynomial like that, that vanishes on x of n, which probably would be 2n. Anyways, then you could prove our conjecture. And you could prove for our symmetrical conjecture, which would be huge. Yeah, so even the n equals 2 case of this conjecture is really, really, really important. I think that's kind of like, once you get the n equals 2 case, you'll be able to do the general case. Just focus on the n equals 2 case. And then it becomes kind of easy to see what this is saying. It's just literally these complicated BK value is just telling you the degree is bounded and the volume of the convex hull of the set of exponents that shows up. It's bounded by x squared. Yeah.
When you mentioned Stark's conjecture earlier and being able to construct the element U,
Yeah.
how much of FAB can you recover from constructing this U?
Yeah, basically all of it.
Okay.
Yeah. Basically, if you have, all the U's for all the extensions. Again, you have to do this trick of throwing in square roots to get fields of all possible signatures. You only get fields of certain signatures when you join these Stark units. But yeah, up to throwing in some square roots and all the Stark units, you get the maximum beyond extension. In that case too. Yeah. Yeah, so if one could prove Kyrie's conjecture, you could construct the maximum abelian extension of any almost totally real field. That means any field where it has all real places except one complex place.
Let's thank the speaker again.